Hello, Poe. I'm Professor K, and this is What is Unification, or Unification Theory. I'd like to preface this video in saying I'm doing this to give an alternate explanation or view of some of the phenomena I talk about here, to provide an alternate visual representation or possibility of the way some of this stuff works. Also, when I mention the term particle, I'm not necessarily talking about a tangible thing, but rather the term particle is a placeholder for some energy signature. Okay, so what is unification or unification theory? Well, in physics, it's about finding a theory to cohesively tie together the four known forces of the universe. Not just to show the relationship as a suggested, oh, it might be like this, but rather it needs to have sound mathematics, and hopefully, and what can be a difficult part is finding the experiments to push or to, support that theory. And this would eventually help us make sense and understand some of these other things better and answer other questions like what is dark matter or dark energy. Now, there are some unifying theories out there, like string theory, which suggests that everything is made of these hyperdimensional strings that vibrate in many dimensions other than are known for, if you include time as a dimension. And there's a lot of math behind this, but that's just one of the I'm sure there are many theories people have out there. That just happens to be a known one. And so in explaining this, I'm going to propose, what could be a theory of how some of this stuff can work, and hopefully explain, dark energy. And what dark energy is if you think of space expanding, if you look back, rewind the clock on time, and show the universe, started expanding. Well, it seems that expansion rate is kind of like picking up a little bit, speeding up. And the galaxies themselves aren't necessarily moving away from each other. It's more like the space in between them is just growing, giving that illusion. Some of them are moving away or toward each other, but dark energy is the expansion of space itself. I like to point out too, when you fast forward the clock on the universe, that what you might call the heat death of the universe, there's this point in time eventually, trillions and trillions and trillions of years, I'm sure from now, where all energy seems to kind of go to zero, where everything kind of eventually becomes nothing but photons, kind of like the cosmic microwave background, and those photons get so stretched out that it eventually becomes the cosmic radio background, and then eventually to nothing, right? So if your light wave or light energy is like this, as the universe stretches out, that wave stretches out, and eventually you're left with a frequency of zero. And what happens to a photon when the frequency becomes zero? Do you still have a photon? Is it anything without its frequency? I mean, in order for something to have this electromagnetic moment, it needs to have some energy. And if it doesn't, is it still something if it doesn't do that? But anyway, tying gravity together, this is a big one to talk about here. And that is, it might seem counterintuitive to think of gravity as right now, me holding my hand out like this. I'm not holding my hand still. I'm actually moving it upward to counter the effects of gravity. I'm putting some energy into my hand constantly so that I'm moving it upward at a speed, because its natural state of rest is to be following the curvature of space and time and to be falling down. So this which looks like I'm holding it still, is actually moving upward, whereas this is actually moving still. It might seem like a counterintuitive. Gravity isn't even a force, or, you know, most people would say no. That is just a warping of space-time. And I like to draw these pictures where you have a trampoline and a bowling ball. You put that bowling ball on your trampoline here, and it warps that fabric. And then you take another ball and you roll it on there, and you say, well, look, see how that ball follows the curvature of the fabric? That's how mass warps space-time. I don't think this is necessarily the best analogy, though. It just doesn't. You're taking a three-dimensional sphere, putting it on a two-dimensional plane, and then you're using the Earth's gravity to try to explain gravity. But the only reason this fabric is stretching the way it is because it's pulling back in the opposite direction. I mean, does space-time have edges to it that are being pulled on? So that's not necessarily the best. There's a slightly better one where you might, you know, try to draw a fabric, if you will, and call this space-time fabric. And then you can put your planet or your star, something of large mass, in your space-time, and then you can show that it stretches and warps that space-time. But again, here, I mean, what is space-time made of? What is actually warping? So gravity is kind of, you know, this. It's difficult to show how something in this place here in space and time, and this place here in space and time, how there's a difference and enough to constitute for this rapid acceleration, if I were to let this go, okay, that we know of as gravity. So taking some of this stuff into consideration, I'd like to propose a unification theory in a way to try to give you an idea of how you could put together something like this. And this is, you know, my Occam's razor, simplest explanation, my little go-to. So I'll start with saying that, you know, space-time might just not be this emptiness or this static fabric. It might instead be filled with some type of ether that might be a little bit more dynamic. So if you zoom into an atom, we'll take a hydrogen atom, like a proton, and it might have an electron somewhere out here, right? Well, the thing is if the proton were actually, if I can draw a little dot here, I don't know if you can see that. If the proton were actually that size, the electron would be, I mean, it would be way, way out here. It would just be, you know, way far away. And so what is all in between here? What is, you know, somewhere there's a signal kind of being shared between the two, an attraction. And so what is traversing that expanse between the two? Now it's really not that big of a difference. It's microscopic, but compared to the relative size of these known particles, that's a lot of space. And so is there anything there? Is there something filling that space, or is it just nothing? So what I like to do is I like to call what you know of as space-time as the c fast. I just remember it this way, as c being the speed of light and it's fast, but really this stands for the continuum, the fabric, the ether with an A, or space-time. Whatever you want to call it, until we actually know what it is, none of these should be considered right or wrong. Okay? So I like to think of it more of as like an ether or some particulate, as if all what you know of as empty space is filled with something. Some very minute, very tiny, very weak, structure to it. But the structure that it has is dynamic, that it can move and shift. Okay? And I see it as, these minute energies. If you look at some small packet of space-time, even in the vacuum of far out space, it seems like there could be some small amount of energy present there. Particles that seem to pop in and out of existence. And what I like to think of is that instead of gravity being just the warping of some static fabric, that perhaps it has more to do with a dynamic current. So if you have a particle, if you have, let's say inside your proton, this is a blown up view of the proton, we have these quarks here. And there are these forces, binding these quarks, these gluons, that they themselves don't necessarily have a lot of mass, but they make up for most of the mass. Their energies make up for most of the mass of the proton. What keeps them forever binding these quarks together? Do these quarks have a natural state of this is just where they want to be? What are these gluons really doing that they're binding the quarks together, that their energies seem to be perpetual and forever going? Or the electron orbiting, right? Does it orbit? But its energy, however, it is in this cloud around the proton. Why does this electron seem to just kind of continue? What's causing this perpetual motion? Now you could say, well, it's perpetual because there's nothing there to stop it. These energies, they are their energies. That's it. But I like to think that some of these quantum motions are the cause for, if this dynamic ether, that somewhere these quantum, say this is your electron and it moves through the ether, the space-time that fills all around us. But as it moves, it can, say, borrow this energy, very minute. I like to think of it as like soapy foam. The amount of energy this takes to like pop one of these bubbles is so tiny, it's like nothing. So for that bubble, for the other, nearby, when that bubble pops, the other nearby bubbles immediately form the new walls of the new one. And so as it's shifting and popping and moving through this ether, this foam, this space-time, eventually what happens is you get enough of these. And you start this current of these new bubbles flowing in. These new space-time particles just kind of moving in to fill in those voids, to the energy that it's borrowing and returning. So the amount of energy it takes to pop the bubble, the new one's reformed, very minute energy replaced, but it just allows that to be that friction, the surface, because the energy is so small. And so as you get, this number increases, then you get more and more dynamic current. And that dynamic current of these tiny energies kind of being replaced as they're being borrowed by the motions of these other smaller particles that creates your gravity. Okay? Again, this is just a theory to try to point towards the next thing I'm going to talk about, and that is dark energy. If you think of this space-time having its own natural, this bathtub filling up with soap bubbles, it has its own natural rate of expansion. These bubbles are so tiny, the number of them you can fit into the smallest of points that you can imagine is nearly infinite. And there's this natural rate of expansion to it where it just wants to keep growing. And so, like I say, this expanding foam, this space-time, might just be what dark energy could be. And over time, you have these galaxies, right? And this is my picture of a swirling galaxy. And, they start moving apart. Well, over time, these galaxies, they are giving off some of their initial mass that they had when they formed. Light constantly being emitted for billions of years. Eventually, you reduce some of those energies, or I should say, reduce the mass of these galaxies ever so slightly. And over enough time, they lose some of their pull, and this natural rate of expansion can just continue to go up, increase. What that natural rate of expansion is, I don't know, but the other way I like to look at it is when you look at black holes. If I draw a black hole here, and a black hole is really kind of spherical shaped. It's event horizon. And because you might see pictures that are like, they look something like this, and they show like some weird saying that this comes down to this like singularity point. What this surface here is, where this is just kind of showing how space and time fold. This surface is kind of like your event horizon here, which is if you took this flat piece and kind of shaped a sphere with it. Everything's being pulled to the center of your sphere. That's what that is. So, but anyway, this gravity, or this ether, I should say, might constitute for why black holes that are larger in size seem to have a lower density. And I think it's perhaps that there is some sort of limit to how much mass or matter that you can have inside there. That at some point the singularity itself might be growing. That there's not some tiny infinite point anymore, that something is growing inside there. Okay? So hopefully, that's one way of kind of looking at, if you have something more dynamic. And so this would be saying essentially that gravity is more like, or matter, I guess. The way gravity affects matter is what I'm talking about here with the proton and the electron being way out here, is that what's filling in this is this ether. And so when you zoom into us, we ourselves are these, particles, and if you zoomed into where, a proton was this big, we would be like the size of the universe. And so as you have this dynamic current due to these energies soaking up these tiny other energies, that's what space-time is, you get this converging flow. And so matter would just kind of be like, a fishnet in a stream. It's mostly holes, but there's some drag on the net when you stick that net into the stream. And so that would also kind of explain why there's such a similarity as when you travel at high speeds, relativistic speeds, why it's similar to being near large, our black hole here, again, sorry, I erased that. Why traveling at high speeds through space is similar to being near the edge of a black hole, because if you have this convergence of space and time, all this space-time is moving through you. And whereas if you're traveling at a high speed, it's doing the same thing. These would only ever move at the speed of light when they're, moving. But as you approach this, and the energies they would have, me moving this slow, they would only go down. Your motion, you'd have to say what this energy is at the speed of light. So as you move through it, that energy drops dramatically. So if you look at the amount of energy on, say, the proton, or the amount of gravity, or the force of gravity on the electron, if this is our proton and this is our electron here, just kind of going around our proton. If you say, what's the force of gravity here? I'm not sure what it is. I'm just going to kind of guess off the top of my head. I might be wrong on this, but I'm going to just say 10 to the negative 47 newtons, okay? Let's just say it's something so tiny that it's nearly impossible to measure. I mean, I shouldn't say nearly impossible. It pretty much is impossible for us to measure this. But this force is so low that if you say, well, what is your frequency? How many bubbles is this popping of our space-time in a second? What's the current flowing in per second to replace that? And if you say it's something like, I don't know, 10 to the 23 per second, that would be your frequency of your space-time ether, or we can call them gravitons, if you will, right? And again, these don't have to necessarily be particles in the sense of a particle, like a tangible thing, just an energy signature, just some very weak energy. But then that would bring, this value, to be a minimum of 10 to the 70, and it would only go down from there, depending on your motion, right, through the space-time. Is this the case? Does it work out? I mean, you could, try to make it work out, but when you look out in space and you see these gravities or galaxies that cause this gravitational lensing, and you see this curvature of space and time around, this bubble, if you will, and the way the light comes to us, it suggests that there's this warping of space and time is definitely a thing. But what's causing the warping? We don't know. We just know it has to do with mass, and somehow mass is doing this. And I'm suggesting here that this would be doing the same thing, warping space and time, because once you get a current like that, anything going through it is going to be affected in a way. You create this pole. So yeah, the energies of the space-time would be so minutely small, it would be impossible for us to measure or detect. Coming up with some experiment to show that would be very difficult. I like to think of it in terms of if you could look at a packet of space and say, in so much space, this photon has its electromagnetic moment so many times. So if this is one section of space, right here. And we say there's, you know, 2 electromagnetic moments here for this photon. And this is, you know, we'll call this low gravity. And as you approach something of high gravity, and you say space and time kind of warps, and then you come back out to here. This here can be our excuse me, did I say low gravity? High gravity. As you approach something of a mass, let's say like a black hole, right? Your photon gets near a black hole, but escapes, right? Does it lose any of its energy? And if it does, you'd have to say, well, if space were static, why should it? Because as space and time itself kind of shrink down or warp, whether it shrinks or expands, it's kind of difficult to tell, but the way it warps, you would still say per unit of space and time, you would still have 2 electromagnetic moments. So each space and time, you would say there's 2. And you should end up with 2 in the end. So when it comes away from that black hole, it should still be the same. There shouldn't really seemingly be necessarily an energy loss to that photon. So if there is, you know, there might be some other reason. But I like I say, I like to think of this warping being caused more by a dynamic space-time. And even having this theory on gravity, you're still left with, you know, so many other questions, like how do fields permeate? What are they permeating? What is the connection there when you have an attraction, or even looking at the electromagnetic field? What is that field, you know, what is that empty space doing to give this effect that we know of as this electromagnetic field? So again, hopefully, you know, this was just kind of a proposition of a theory. But unification in physics is about tying this stuff together, explaining some of this stuff, and hopefully having a decent theory that you can show mathematically. I think we have a lot of the math out there. It's just refining the experiments and refining some of that, being able to get better at testing some of these things. I don't know, you know, how much further we can go, but that's what unification theory is about. And maybe you'll have a better one. Maybe you'll have your own, you know, better theory. But yeah, that's what unification is, and I hope you got something out of this video. Again, I like to show things in kind of a different view, different light. If you'd like to see more stuff like this, again, you can always like and subscribe. I'd like to talk about other issues, like, you know, can we have a warp drive? You know, what is intelligence? Or, you know, teleportation, can we do that? Those type of things, you know, try to put some light on it. So anyway, I'm Professor K. Thanks for watching.